Here is a classic related rates problem. So here's the question. You're walking away from a light source at some speed, and you want to know how fast is your shadow's length changing. There's a standard method to solving a related rates problem. It's 4 steps. So step 1 is draw a picture. Right? You're told some sort of story. You should convert it into some diagram. Step 2, to find an equation. Given that picture, you should label everything in the picture so you can write down some equation. Step 3 is to differentiate that equation, which will probably involve the chain rule. And step 4 is to solve that equation for whatever you're interested in finding out. I mean, you're hopefully trying to find some rate of something, so you're going to try to find one of those derivatives in there. Let's draw a picture to represent this person moving away from the light source. Here's my picture. I've got a light source right here, and I've got this person right here, and I imagine that person walking away from the light, and I've drawn in their shadow, and I've drawn this beam of light just glancing across this person's head. Now we'll turn this picture into an equation using similar triangles. You might suppose that the original problem told us that the lamppost was 3 meters tall and the person was, say, 2 meters tall. And then I can label the other relevant lengths in this diagram. I'll call x the distance from the bottom of the lamppost to the person's feet, and the distance from the feet to the tip of the shadow, I'll call that s for shadow. So now I've got a nicely labeled diagram, and I can replace that nicely labeled diagram with a slightly more abstract diagram where the person is now a vertical line, the lamppost is now a vertical line, and I've got these triangles. The upshot here is that I've got similar triangles. This little triangle is similar to this big triangle, well, because the angles are all the same, right? Both of these triangles have a right angle here. They have the same angle here. Consequently, these angles are the same. There are 2 triangles that have the same angles. They're similar triangles. And as a result, I get this equation out of the diagram. This distance to this distance, x plus s to 3, must be the same as the corresponding ratio in the other triangle, which is this distance to this distance, s over 2. With an equation in hand, we can now differentiate. Thinking of my position and the shadow's length as a function of t, I could rewrite this equation as, say, x of t plus s of t divided by 3 equals s of t divided by 2, right? My position is a function of time and my shadow's length is a function of time. And I can differentiate both sides of this equation. The derivative of this is 1/3 the derivative of x plus the derivative of s, and the derivative of the other side is 1/2 the derivative of s. And now I could solve for the derivative of s. Let me first expand this out. I've got 1/3 derivative of x plus 1/3 derivative of s is 1/2 derivative of s. I'll subtract 1/3 s prime from both sides. Got 1/3 x prime is 1/6 s prime, because a half minus a third is a sixth. And then I'll multiply both sides by 6. So I find out that s prime, this is the rate of change in the shadow's length, is twice x prime. This is the speed with which the person is moving. There's a bit of a surprise to this answer. Take a look at this equation. It's telling you that the speed that your shadow's length is changing is just twice the speed that you're walking. But it doesn't matter where you're standing. The value of x doesn't appear on this side. Only x prime appears on this side. So that's kind of interesting, right? The speed with which your shadow is growing only has to do with how fast you're walking. In fact, the speed with which your shadow is growing is exactly twice the speed with which you're walking, assuming, of course, that you're 2 meters tall and the lamppost is 3 meters tall. I think the important thing to take away from this example is that similar triangles are hugely helpful. If you see similar triangles, use them. There's also one thing that I think is very funny about this particular solution to the problem. Here's the challenge for you to think about. If your velocity is 90% the speed of light, so you're almost going the speed of light, then this formula would be telling you that your shadow's length would be moving faster than the speed of light. Is that really possible?